Just confirm if my voice is audible. You can hear me. You can see the screen. All these three things. Okay. Thank you so much. So, good morning or evening, everyone, depending on where you are. And let's get started with session 5. So, in the last week, we discussed about 6 layers of context. We discussed about what is the system prompt constituting. We discussed about RAG in detail and also MCP, Model Context Protocol. Today, we'll be primarily looking at 2 things. One is the compress part of the WSIC or WSCI architecture. W is a write, then isolate, select, compress. So these are the 4 parts. Select part is RAG. Write is creating the memory, persistent memory or short-term memory. Also creating scratch pads using task.md. And compress is something where you have a context window which is getting populated as you keep using the large language model. And then you want to retain certain information and you want to remove noise. So compress is an operation which can basically do that. And in Cloud Code, for example, the way it is done is using the /compact command. And isolate is something which you will be very interested to learn about, because here we will discuss about sub-agents. So if you have ever used Cloud Code or any other agentic coding platform, you will see that sometimes it will automatically spin sub-agents for different tasks. Sometimes the tasks are in series, they are serial tasks, and sometimes they are parallel tasks. And you know that it speeds up the execution by a lot. So we will discuss how exactly is context window constructed in these cases. What happens to the context window when you compress? Is there loss of information? If yes, how do you mitigate it? Or do you even want to mitigate it? And if you are isolating the context, what does that mean in terms of what happens to sub-agents? So sub-agents have isolated context, and some part of the context is also shared. So we will see how from the perspective of context window, how these concepts work. So just to reiterate, a write part is something where we decide or we tell the model that if you are working on a subtask, create individual task.md files, and these task.md files will have to-do nodes, and those to-do nodes will make sure that for each task, the model is at any given point of time focusing on the subtask. So if the model is at the same time building front end and back end separately, or let's say you are working on a research agent where one agent is running certain experiments, another agent is running some literature review or finding the gaps in literature or something like that, then they can have their own short-term memory, they can have their own subtasks, and then those tasks will be finished separately, independently. And select layer is selecting what you need into the context window from outside the context window. So from outside meaning it can be from a database, vector database, it can be from just a file system. And retrieval augmented generation selects things out of the context window to be considered to the context window. And in the WSCI framework, compress and isolate is what we will be looking at today. Okay. And this isolate part is where we will discuss about sub-agents. And this is something that we have discussed many times. The reason why we want to compress is twofold. One is when you are compressing the in the next round of iteration, the agent is getting smaller number of tokens in the API call. And oh, the screen is blank. Do you all of you are seeing the blank screen? Can anyone confirm if you see the screen or if you're okay? Okay, thanks. So what I was saying was the reason why you want to compress the context is because you need to reduce the number of tokens that are going into each LLM API call. So let's say I have a question. Okay, this we will discuss in detail after a little bit. But basically, say we have one agent, and just let me just stop some background processes. My computer is becoming a bit slow. Just give me a second. All right. So I hope everyone should be able to see the screen now. So you have one agent, and let's say this agent is making a API call. Can you tell me the cost of your large language model usage? What is it dependent on? Is it dependent on the number of API calls you make, or is it dependent on the number of tokens which you consume? Let's say to one LLM, you make 300 API calls. To another one, you make 20 API calls. All right. In the first case, you consume, let's say, 10,000 tokens. In the second case, you consume 200K tokens. In which case do you think you end up paying more? You're basically build based on token consumption for input as well as output. So it doesn't matter if an agent is spinning sub agents who can make their own separate API calls, as long as you're managing your total token consumption in the form of an optimized context window really well. So it doesn't matter that you give your sub agents ability to make its own API calls, as long as the context window for that sub agent is very minimized. It's minimum number of tokens. So for two reasons, you need to compress. One is, of course, to minimize cost. Second is to minimize the rot of the context. Because imagine you have only one agent for doing every single task. That agent will basically, let me just allow certain people into the meeting room. Yeah. So if there was only one agent doing all the tasks for a project, what will essentially happen is that agent will eventually experience context rot. So beyond certain point, there is too much information in the context window to process, right? This we have discussed a lot of times. So there are largely four types of compression. First type of compression is the most obvious one, or probably the most powerful one. Not necessarily the most cost optimized one, but it is summarizing the context window using a large language model itself. So what you could do is, so one of the most popular context compacting or context summarization methods that is used in cloud code is LLM-based summarization itself. So you make another API call to which you pass the context, but ask the model to summarize the context into certain number of tokens. So if the context window size is 200K tokens, and you have reached, let's say, 80K or 100K tokens already, you could ask /compact. You could run the operation /compact, and then the context can be compacted to much smaller size. Often these coding agents also have 80% context window limit, where if the context window reaches more than 80% of its total limit, it will start an auto compacting operation, and which will be based on LLM and which will be much efficient. But sometimes, if let's say in the next output, in the next iteration of API call, the output created is so big that context window exceeds 95% of its capacity, even more aggressive trimming will happen, meaning some parts of the context window will be aggressively deleted. All right. So we will discuss this also in an interactive way when we are getting into the lab exercise. Do we have any easy way to calculate tokens for large context? Yes. So at the end of the day, context will be having two types of things: structured inputs from JSON files or other file formats, and natural language inputs. On an average, one word is equal to one token. So that is one way to see. I mean, for hand calculating, if you want to hand calculate how many tokens have you consumed, just count the number of words. Otherwise, ChatGPT itself has a context um, um, token size calculator. You can just Google ChatGPT or OpenAI token length calculator. They provide a window into which you can paste whatever input you have, or whatever text or whatever your context window looks like, that you can copy paste, and it will tell you exactly how many tokens are you at right now. And in cloud, usually the context window size is 200K tokens, which means if you are at around 160K tokens, you are in some sort of not yet in the danger zone, but you are at a zone where you would want to perform some compaction. So the way I work is, in cloud code, the auto compaction happens whenever the tokens have reached 80%, meaning if it reaches around 160K tokens, you will see that auto compaction automatically starts, which is based on LLM. So it will make another API call and that API call will semantically compress the current context into much smaller section. I will show you the details of what are we compressing. There are tool results, there are system prompts. What exactly do we compress and what exactly do we not compress? And what are the after effects of this that we will see. But often in my execution, what I do is I do two things. One is if I'm completely switching from task A to task B, where I don't want any relation with, I don't want to be any memory from task A to be carried forwarded to task B. I just put the operation /clear. And I have noticed in many type of tasks, this provides significant improvement in the output quality. Especially if your quality you observed is to be degrading, you have to do a /clear operation if there is a clear distinction between two tasks and they are not sharing anything in common. However, if the task is slightly distinct and you think that a lot of the things that are accumulated in the context window so far is because you have been carrying out a lot like a long operation and the context window is having a lot of tool results. Let's say you were running paper banana to generate images and you are having 17 images to generate. And then in these images, basically you have provided the descriptions of images, but then by the time you are reaching for 15th or 16th image, your context is so bad that the sort of images that are generated are very bad. Then at that point, you can decide, okay, I don't want to lose the overall context, just do /compact and then continue generating, and you will see a significant step function, like a step function, the improvement in quality of the output. So first type of compression is summarization. Second is called tool result clearing. Can anyone tell me what is tool result clearing and why can we simply clear the results of a tool call? Why is it not problematic, or is it problematic? If yes, why? If not, why not? So and in simple terms, first of all, okay, let's go step by step. What exactly is tool result? You can refer to the discussion we had in the last lecture, right? So a simple example is, let's say the MCP server is sending some sort of structured result as a result of invoking of a function. So a tool you can imagine to be a function, or it can be an API call which executes certain function or fetches something from the database. At the end of the day, there is some input going into the tool. Tool is providing you some output. Output might be in a structured JSON format or in any other format. Now, you might notice that in many cases, this output will have so many things. It will have just-in-time instructions. It may or may not have verbose results, like which is like very detailed, because often LLM, for it to use the tool results, it need description of the structure of the result, plus the result itself. So it will be very big document. Now think about this. Is the result of a tool execution, is it stochastic or is it deterministic? Like if you run a function with a certain arguments, okay, do you expect the same result with if the arguments are the same? Typically, functions are such that the result of the function is dependent on only one thing, which is the input or arguments going in, which means there is great deal of deterministic nature when it comes to tool results. So, of course, it depends on the functions, whether function itself has a stochastic nature, but in general, the functions, if you want to mimic the results of the function which you got earlier, and if you are in such a dire situation that your LLM context window really needs the result from a particular tool, it can simply run the tool call once again, right? So there is no need of storing the last previous tool call results in the context window continuously. You could simply entirely delete the tool result, or you can simply compact it into few sentences. The tool result, which may be in multiple lines, maybe in JSON format, can be compacted into simple natural language 2 or 3 sentence summary. In some cases, if you are aggressively trimming, which is what happens in a concept called priority-based trimming, the tool results have it's of one of the lowest priorities, which means tool results will be aggressively trimmed. Trim meaning entirely cut away. It will not be part of the context. But Cloud Code does not use this that often. The most common two compression methods used by Cloud Code is LLM-based compaction and tool result clearing. We will see this with an example, how it visually looks like, how the context window visually changes when we clear the tool result. And the last one is, so in priority-based trimming, we just assign levels of priority, P0, P1, P2, P3, etc. P3 is something with the lowest priority, and P0 is something with highest priority. Highest priority meaning it will be the one to go last. It will be trimmed the last. Now, based on all the things you know, what could be P0? So P0 is, let's say you have examples, a conversation history, system prompt, then tool result, then maybe some custom instructions for the agent. What could be P0? So one of the highest priority items by default is system prompt. System prompt is the last to go. System prompt will often have rules, right? So system prompt is definitely not P3. What could be an example of P3 other than tool results? So tool results, yes, it can be of low priority. What else could be P3? So we can define P3 in the following way. For example, let's say we had a conversation history from many context windows, not context window, many conversation windows before. So if we define one conversation window to have X number of back and forths, a conversation which happened much before can be significantly summarized or completely trimmed away to preserve the context. If it comes to trimming, by the way, trimming does not happen in Cloud Code unless you are at 95% of your context window filling. If context window has filled 95%, this will happen. Otherwise, trimming is not done. Okay. Can you give me one more example of something other than system prompt, which you may not trim? That I will come to in this hierarchical compression. So in hierarchical compression, using semantics, you will decide what has the highest priority and what has the lowest priority. And whatever is the highest priority will not be removed. Whatever is the lowest priority will be removed. So in hierarchical compression, to decide the hierarchy, you are using semantic meanings. Here in priority-based trimming, you are using rules to decide what comes in P0, P1, P2, P3, etc. So can you tell me something that can be at the highest level of hierarchy, meaning something that will be removed last, which is not system prompt? Okay, many people are saying user prompt. Okay, for sure, user prompt is something valid. You cannot delete user prompt just like that. But my question is, let's say user gave a prompt, LLM gave an output, for example, and that output is now output tokens are now added to the context window. What type of output might come at the highest level of hierarchy? Something which you should not delete or something like that. It could be something like an output where after this output, the user is supposed to give a preference based on the output, right? So for example, let's say you're building a website and your phase one is being executed. In phase one, you have explicitly told the coding agent that at any point, if you feel like you need my input on the user interface or user experience, or the way you have to arrange your cards in the front end or something like that. And let's say the LLM is supposed to receive an input from the user after it produced its latest output. So LLM might have produced let's say, a skeletal structure. Now to add meat to it, a user instruction needs to be provided. And for user instruction to be provided, it is very important that the LLM retains the immediate previous output, right? So that immediate previous output, which the user has not yet seen, or the user is supposed to comment something on, should be kept while doing compression. And how does the LLM know whether something is of such high relevance or something is of not high relevance? Simply by making another LLM call and another API call. In that another API call, semantic meaning can be associated to different parts of the current context window. Based on the semantic meaning, You decide the hierarchy. And what you do is, if you are at the top of the hierarchy, 100% of the items are retained. If you are in the next level of hierarchy, 70% of the items are retained. If you are in the next level, 50% are retained. If you are in the last level, only 10% is retained. So if only 10% is retained, this could be most likely tool called results. So if you are compressing your tool called results into 10%, it simply means your tool result will become a 1 or 2 sentence summary. All right, so this we discussed already. So in LLM summarization, if you have a long conversation history between the user and the assistant, you simply convert it into natural language summary. So structure might be lost. Some nuances may or may not be captured. But the goal here is most of the information or most of the facts which are there in this conversation should be ideally captured. And there is something called IRR, information retention ratio, which is if you decide that if you can say out in this initial context, there are 30 information which can be mentioned in bullet points, which should not be removed. If all the 30 can be recovered even after compression, then the IRR ratio is 100%. If only 90% can be retained, so is the IRR. So then basically it's a lossy compression, right? Compression is always lossy. Sometimes the loss that happens is something that is not relevant. Many times you want to make sure that the facts which are quantitative things are retained. In tool result clearance, this is what I showed. Tool result will take you from large number of tokens being consumed to very, very few number of tokens being consumed. This we can visualize when we come to the implementation part. And this is the most common thing, which even if you are not using Cloud Code, even if you are constructing a coding agent yourself, one thing you should define is how tool results are cleared or compacted. This we already discussed, when to remove which are of highest priority. So system prompt is of highest priority, never removed. Core instructions to your, let's say, which is there in the root folder agent.md file for the agent instructor, agent orchestrator, or core instructions for the which are defined in the cloud.md file, they are not removed. Tool definitions, which may be part of cloud.md file if the number of tools are less, or tool definitions that are currently living because RAG fetched the tool definitions from your database are also again not removed. There is a question. We are not counting thinking tokens at all because thinking tokens are not at all included in the context. Like they are just part of test times scaling, but not really included in the context. You mean in reasoning models, right? So one thing we can do is, yeah. So yes. So typically thinking tokens, to my understanding, it is also included in this context window, because at the end of the day, if it is a chain of thought, for chain of thought to propagate, you have to have the previous output which was produced as part of chain of thought to be added in the context. But one more thing you can do is, in the last week, we had a brief discussion last lecture or last to last lecture, we had a discussion about should you always have reasoning based large language models for React to be implemented. There, it's not really necessary that you need reasoning based large language models. You can invoke behavior similar to reasoning with non-reasoning LLMs also, just by relaying its output in the form of reasoning. So you force the LLM to come up with a reason, then coming up with an output, coming up with a user output, and then go 3 or 4 loops of that before giving the final output. Is there any lecture around it? You mean a lecture around reasoning is itself? We don't have a specific lecture around reasoning, but the basic idea is that the tokens that are consumed during reasoning, tokens that are generated in the output as part of reasoning, is also consuming the context window for sure. Then, yeah, so the current, okay, first of all, let's see this. Older history, this could be part of conversation or part of, let's say, summary of the tasks that are completed you don't need. Tool results, stale tool results mean tool results which were produced earlier, which is not useful anymore, not needed. This compress if needed is, this is this is not done always. This is only in extreme urgent cases where you actually have to trim some recent conversation also. So you will clear the recent conversation and recent tool results only if you absolutely have no space in the context window, right? Older conversation history and older tool results are cleared first. Then current task context, current user query, and current action plan. These things are again having very high priority, which means this will not be removed. System prompt is always kept. Then in hierarchical compression, this is what I said. Hierarchy is decided based on semantics. So if hierarchy is of the highest, 100% is preserved. If it is important, 50%. And if it is in the lower part of hierarchy, 10% or only 0% is kept. This I have already discussed. Okay, is this how coding agents are designed today, like Cloud Code? Yes, exactly. So in coding agents, you don't have to define how compression works because these principles are already inbuilt inside the coding agents. However, coding agents are at the end of the day, these instructions wrapped around an already existing LLM, right? So already existing LLM is Opus 4.6, for example. Around that, these things are built. And that is how Cloud Code is built. However, if you are using OpenClaw, you might have noticed that when you install OpenClaw, they give a long set of available LLM options. So in OpenClaw, when Pete Steinberger was building the OpenClaw framework, he has followed many things that are mentioned over here. However, the only difference is there it's not primarily a coding agent. It's primarily a agent which can act as a personalized assistant. Yeah. So hierarchy-based assistance trimming is basically this. Inside the context window, instead of saying, hey, tool results have lowest priority, system prompt has highest priority, or old conversations have low priority, new conversations have high priority. Instead of explicitly saying that, you let an LLM figure out based on the semantics of what is there in the current context, decide which part of the context is highly relevant, which part of the context is highly not relevant. In the previous one, which was trimming based on priority, there is no LLM involved in deciding what is recent, what is relevant, etc. Relevancy is decided based on the structure itself. So in the structure, if there are tool results, which has a timestamp which is more recent, you can decide a cutoff. Tool results from the last 10 invokings of the tool are not part of the are part of the context window. Everything before that is thrown out of the context window. So you are deciding a cutoff based on just some logic which is predefined. However, in hierarchy-based compression, it's not trimming, by the way, it's compression. So you are not entirely removing nothing much, but you decide that this is the hierarchy of different sections of context. If something is at the highest part of hierarchy, you don't trim it, you keep it 100%. As you go down in hierarchy, you assign lesser and lesser importance, which means you summarize it more and more. So higher and higher compressions are applied. So finally, when it comes to the lowest level of hierarchy, you may compress it to 5% or 0%, so that almost nothing is kept. Maybe a one sentence summary is remaining. And as you go up the hierarchy, you will see everything is retained pretty much as such. So one more thing is when we are performing compression, it is expensive because you can't keep on compressing. See, if you want a clean context window, you could ask, then why can't I keep on compressing every single time? Why do you not do that? Why do you not compress the moment, let's say you feel like your context is growing? Why do you wait for 80% cutoff to happen or 95% to happen? Why not always compact? Or why not always clear the tool results? Always compacting is anyways not good. You will compaction all by definition, it means you are losing some information. But at the same time, you have to call the LLM, you have to call some sort of LLM for most common type of compaction, which is LLM-based summarization. And that is expensive, right? So now imagine it will be double as expensive because your context window is 200K tokens. You are then calling the LLM for compaction, which means another 200K tokens are consumed. And that LLM will provide you some output. Maybe that is like 10K tokens. That 10K tokens are now used to represent your original context. So apart from your original 200K tokens, which were part of the context, let me just draw it. So let's say this is your original context. And maybe, so this is 200K. and only 100K is consumed so far. Now you make another API call to the same LLM or to a different LLM, depending on how your structure is. Into that LLM, you will pass the same context and provide instruction. So instruction will be maybe this much on how to summarize. And then that LLM will produce the summarized version of this, right? Summarized version of this may be only these many tokens. Now look at the cost associated with this. To compress this much, you are consuming so many tokens. And then what you will do is this compressed context window will replace this 200K. Now this, if 200K out of this 100K is consumed, now this compressed section, this will replace our context window right now. So yes, you compressed by 90%. You went from 100K tokens to 10K tokens, but at a cost. The cost is you ended up consuming these many tokens in a separate API call. Plus you will introduce, of course, as somebody mentioned in the chat, latency, because each time you make this API call, you're waiting for the results to come so that you can replace the results with this in this compacted context window. So you don't use this very, very often. Okay, very good question about how do you choose the best model for compression. So typically for compression, you don't need a proper coding based model. You just need a model that is good at language in general, because LLM based compression is basically compressing most of the things into summary sentences. So it needs to be really good at natural language. So even if you are using Claude code, I don't know how it internally does this compression, whether the model is different or not, that I have to check. But if you were to implement something like this manually, you can use your best model for dealing with your original context window. And for compression, you can use a lightweight large language model so that at least API call you can minimize. Latency will still be there. Sometimes you can also compress based on some sort of keyword based extraction. So you can, from this context, based on keyword, you could extract the required portions, and that required portions to be converted into a meaningful format. You can pass it into a separate API call, which means you are not consuming like 120K tokens or something like that. You may consume like 30K tokens, and then that can be compressed into 10K. So this is the idea of compaction. But there is one more concept that we need to discuss apart from compacting the context, which is splitting the context across different agents who are performing different functions. Let me just check if anybody is waiting in the waiting room. All right. So in Cloud Code, we don't have to mention explicitly what the compression technique is. By default, it will be using LLM-based compaction and tool result clearing-based compaction. Those are the most commonly used. You don't have to explicitly say. However, for whatever reason, if you want Cloud Code to use different type of compaction, because you would say, hey, you are an auto research large language model. Actually, why don't I show you something? Let me open my Visual Studio Code. Just give me a second. I'll stop sharing the screen for a moment. All right. So do you see my Visual Studio Code right now? Just if you can confirm with yes, that'll be great. Are you seeing Miro board or Visual Studio Code? Okay, thanks. So basically what you're seeing right now is one of my workspaces where I am using a continuous research agent to explore one problem statements that we are working on at the moment on vision language action models. Okay. So this agent, I will just show you this agent. It was released by Andre Karpathy in last week. It's called Auto Research. So basically what this agent does is, and this has blown up, by the way, in terms of number of stars and all. Last time it was 30K. In one day, it has gained 6K, 7K more stars. But basically what this agent does is, so he shows in this graph, agent will conduct research and it will figure out what kind of experiments to done, what kind of model architecture changes to bring to better your results. So I just wanted to see if we are running some experiments, if we ask this auto research agent to conduct our own research, or conduct its own set of experiments, will the accuracy, or will the metrics that we are tracing, will it keep on improving, and what will happen to the expenses, etc. So here one comment which I had provided explicitly to Cloudcode while defining the its purpose was, I am worried that my context window might rot because you are working on so many different tasks, one after the other sequentially, in the process of running these experiments and writing the paper. And because of that, I'm worried that you may even hallucinate some results or hallucinate some experiments. So then what I did was this, I explicitly mentioned, like whenever you decide to do a new set of experiments where you feel like the previous set of experiments are in a completely different sandbox, and the new experiment can be considered to be a different sandbox, even if your context window is not bloated yet to 80%, just make sure that you are doing an auto compaction. So with this, because of this, in none of the sessions, although this was running 24/7 for last, so I started this experiment on sometime on Saturday around 2 p.m. or something like that. Although this was running 24/7 for the last almost 2 days, never ever it ran out of the session limit. So as you know, if you have used Cloudcode, it has a session based usage limit, and then after the session it will refresh. But that never happened with this, and I was keeping on, and I had asked it to push it to my GitHub. So it was keeping on pushing the experimental results to GitHub, and I was tracking the experimental results on GitHub, and not even once it stopped. One way in which this could have stopped is I had given it my runpod access through runpod API, this access token, I think API, not access token. And then I had around $100 in the runpod. I had recharged runpod credits. Only if the $100 ran out for whatever reason, it would have stopped. Otherwise, due to context issue, it would never stop or it would never rot. So yes, I am on a $200 cloud plan because I use it very much extensively for building products and running different experiments. Plus, multiple people in my team use the same account. So we have total 3 accounts, which are maybe used by 7 or 8 different people. So if my credits run out for a session, I just switch the account. So that's what I do. It's not ideal, but that's the only option right now available. So what is done is, if you have a big task, a big project, there will be a lot of files which are actually relevant. All those files, obviously, you cannot fit in the context. And this is where you define sub-agents by giving isolated context to these agents. So how did you ensure context did not blow up? I simply gave an explicit instruction. The explicit instruction was that whenever you are switching task, whenever you are going from one experiments to another set of experiments, even if the context has not reached 80%, you compress the context or run /compact operation. So this will ensure that when I'm running from one experiment to another, all the baggage from the previous experiments are not carried forward. This will significantly keep my context clean. Plus, it will also keep my price a little bit low, price or token consumption a little bit low. I mean, there are many different ways to do this, by the way, but this is what I tried because I was so worried that this may not run 24/7 simply because session usage might exceed, because that has happened many times. But not even once it did exceed the session, although it was continuously running experiments. One thing might be because the experiments are actually run on runpod GPU and not by Cloudcode itself locally. That is one reason, of course, why too much consumption is not there. On the other hand, if you are building a website or something, all the files, node modules, packages, you are literally defining locally. So lot more tokens might be constructed in, let's say, web development compared to in actual research. Because in actual research, you almost never run your code in local Python. So the Visual Studio screen which you saw is not my computer. It is an AWS EC2 instance with some 32 GB RAM or something which I purchased because I needed RAM because I need to run multiple agents on that same computer. So the computer should not slow down. But at the same time, many agents do not run the experiments like building website or running Python script on EC2 itself. So I have connected the EC2 with runpod. So all such heavy experiments are running on runpod GPUs. So because of that reason, one, my AWS EC2 instance does not slow down. Second, my token consumption of Cloud Code is also not that high. But that's an artifact of what type of experiments I am running. But if you are running some experiments where you are running Python script locally in EC2 instance or your Mac Mini or whatever device you use or your computer, I'm 100% sure after some time if you are running 24/7 experiments, your session memory will run out. I forgot what is the total usage, total number of tokens that you can very easily see by typing /usage. In /usage, they will show a bar whenever usage is about to exceed the session limit. Then, okay, let me ask you a question. This, I think many of you may have doubt about. If we, okay, I'll answer one more question. Did Cloud Code figure out how to use runpod API so that you can steer it from your EC2 project? No, Cloud Code did not figure out automatically. I mean, API key, of course, I gave Cloud Code, but other than that, Cloud Code, it's very basic. Cloud Code already figuring out how to run runpod using its API is a very trivial thing. I don't know if it has MCP or just API calling is enough. I don't think it's MCP, it's just API key based. So that part was very easy. You can just give the Cloud Code access to your runpod and ask it to execute the code, store the results, and keep the inference. Those things, keep it on EC2 instance. Runpod, you initiate the pod on runpod, run the experiment. Once the experiment is done, once no immediate experiments are planned, just close it, terminate the pod so that you are not accumulating cost. One day it so happened that I was not using Cloud Code and I was manually running runpod instances. And then what I forgot to terminate it. Then in 2 days, we had some, I think, $150 or $200 bill for nothing. I mean, we were not running any experiments at all because there is some idling cost also for storage. So if it goes for certain number of hours, by default, I think it's $0.8 per hour or something like that for most of the pods. But for expensive pods, for more storage, it will be higher. So even if you are not running any GPU instances at any given point, you will still accumulate some cost. So if you are not running anything, you have to terminate it or pause it. So what I have done these days is I initiate the pod as and when I need. For new experiments, I tell Cloud Code, one of your tasks is to minimize my run pod bill. So for that, but at the same time, it should not impact the quality of your experimental results, because if you need to use the same pod again, you can use that, but make sure that you are minimizing my bill. But if you don't have to keep a pod in idle state for 1 hour or 2 hours, if that is what is needed, in that case, you terminate the pod, you restart a new pod when your new experiment has to start. But whatever results you have from pod number 1, store it in the EC2 instance so that it can be passed if needed into the run pod instance number 2. So these are some instructions I have given. I don't think such extensive instructions are needed. I just gave this as a safety, but if you want to just run the run pod with minimum cost, you can just say that in simple, plain English, and Cloud will most likely take care of it. Last week, I remember one question was, if you have two agents, agent number 1 and agent number 2, okay? Let's say Cloud Code is spinning two sub-agents, agent 1 and 2. According to your current understanding, what happens? Do these agents access the same LLM and same context window, or do they make separate API calls, and they have separate context windows? Plus, one more question is, do they share anything in the context window? Is some part of the context window of agent 1 also accessible to agent 2 directly? Like, is there some way of sharing the exact same tokens which agent 1 is using and which agent 2 can also use? So ultimately, all the sharing happens through agent orchestrator. The individual agents do not share context window directly. Why? Because they are completely separate API calls. So context window of agent number 1 and context window of agent number 2 are two different things. However, if, for example, system prompt needs to be provided to both agents, which means the tokens corresponding to the system prompt, which are stored in agent 1, and tokens corresponding to system prompt, which are stored in agent 2, may look very much the same, because a tokenizer that is converting system prompt into LLM's tokens will be applied similarly. So let's say the Cloud.md file is to be entirely present in agent 1's LLM API call as well as agent 2's API call. Then the way in which that Cloud.md is tokenized will be the same, because you are using the same LLM, same tokenizer. So the tokens that represent the system prompt in the agent 1's context window will sort of mimic the tokens that represent the system prompt in agents 2 context window. However, just because they are mimicking each other, it does not mean that these two agents are sharing it. It may appear like that, but there is no direct sharing. If at all something needs to be shared, what happens is this agent orchestrator will decide what to be fed into the context window of both agent 1 and agent 2 apart from system prompt. So if agent 1 has bunch of results which are given stored back into into the orchestrator's memory, and then orchestrator decides that actually that needs to be part of agent 2's context also, then orchestrator can share it to agent 2. So I'll just show you one figure which you should remember, this one. So these agents directly do not communicate via a shared memory, but rather an orchestrator. In this case, you can imagine orchestrator to be Cloud Code itself, agent A and agent B to be sub-agents spun by the Cloud Code. And Cloud Code should decide what files or what database is shared between agent A and agent B. They don't directly do it. So just please understand this. Now, coming back to why do we need sub-agents? The need for sub-agent is very clear. You have different tasks. So if you are working on a research, you could have an agent that is whose sole purpose is executing some code, Python or JavaScript or some type of code, which may consume a large number of tokens. But this code agent need not, let's say, review the results of the code which it wrote. Maybe a code agent can write the code, a testing agent can execute the code and test it for various use cases. A review agent can review the results and the code, and then this review agent its only purpose will be, it will be provided a code, it will be provided the test case results, and then the review agent has to provide a detailed summary which consumes maybe 2000 tokens. So orchestrator agent will also have same context window size, 200k tokens, but it will not consume 200k tokens. It will consume only 10k tokens. Then it will delegate a task to this research agent. The research agent will consume maybe 40k tokens. This 40k tokens plus 60k plus 30k. So then 100k plus 130k plus 155k, 165k. So roughly 165k tokens are consumed, but they are not consumed within the individual orchestrator agents API call. They are consumed overall. Now this 160k tokens, 165k tokens could have been consumed within one single agent. Okay, but then the problem that would have happened is if the same agent is looking at every single thing, there is heavy context rot. Here that is not there because this 10k is now part of 200k. This 60k, this 40k is now part of another 200k. There is no chance of context rot. Code agent another 60k as part of another 200k. And the LLM does not penalize you for making new context windows. LLM only care about how many tokens are consumed through its input and output. So it's always better to consume these tokens in a modular way by making multiple API calls if that is what your application demands. So these delegates are basically sub-agents. And if you really notice what the Cloud Code is often echoing, it provides an echo, right, as it is performing some operations. Especially in this auto research, I have seen many times it is spinning its own sub-agents. It will say 4 parallel tasks are running right now, if it is working on 4 different figures or something. And then it will say 4 tasks are running. I will give a summary once the task is done, when all 4 agents are done executing the task. So, but the total token consumption is again not very significantly high. So this I have noticed, I have already mentioned. Then what the orchestrator decides, this I will show you in a folder structure rather than in the text format. Okay, so let's see this folder structure when there are sub-agents. Cloud.md, all the agents ideally will have access to, not that it will not pass the entire Cloud.md into the context. It will pass whatever sections of Cloud.md from using RAG or using keyword matching. Then what's the difference between this agents.md and this agents.md and this agents.md? What's the difference between these three? First, let's talk about this one. What is this agents.md? What could this be called as? Can you compare cloud.md and this agents.md? They are different. This agents.md is present in the root of your directory. Your root directory is my project. This agents.md is present in that. Now, maybe the purpose of this agents.md is to help your cloud code decide when you need to spawn new sub-agents. Now, let's say there is a sub-agent whose only purpose is to build the website. Now, this agents.md, which is one level below in hierarchy, will decide that, okay, I am an agent who's supposed to manage this entire website development task, for which there are front-end tasks and back-end tasks. Then this agent will decide, okay, I need to now create front-end tasks. So this front-end folder is there, inside which there is another agents.md. Now, this agents.md is the lowest level in hierarchy, meaning it has only instructions related to maybe the front-end schema or whatever, the components inside the front-end. So now the question is, let's say for whatever accidental reason, you had given some front-end related information over here. You say, I prefer a modern front-end. You mentioned here, okay? You should not mention, but let's say you ended up mentioning. But here you give some other instruction. Here you say the front end should look like monospaced, some sort of legacy style should be followed or something like that. What will be followed? Will this be followed or will this be followed? Will the root level agents.md's instruction be followed, or will the sub agents instruction will be followed? So whenever there is a conflicting instruction, always the instruction provided by the child is used. The reason is simple. The child has more proximity towards the task that is being implemented at the moment. So if front-end is being developed at the moment, this agents.md is more close to the front-end related task, whereas the agents.md on the root level of your working directory is not a front-end specific agent. So it may have mentioned a few things, but it would not have been specific enough, or it would not have been deep enough into one particular task. However, does it mean that the root level agents.md is replaced by the child level agents.md? Is some sort of replacement happening? If not replacement, what may happen? This we had discussed 2 lectures before. If it is not replacement, what is happening? What is happening, you can sort of imagine to be some sort of concatenation. Conflicts are replaced, but otherwise, the system prompts which are there in cloud.md are concatenated with sub-agent level instructions. And that whole thing is passed into the context window of the particular front-end agent. So here, effectively, 4 agents will be there. 1 agent at the root level, 1 agent at the web development level, 1 agent at the test level, Then under the web development, there will be two more sub-agents, one at the front-end level and one at the back-end level. This is how the folder structure will look like. So each of these agents will make its own API calls. Now, the frequency with which the agents may make API call might differ. So in most of the implementation steps, whichever agent is implementing that particular task, so if front end is being built at the moment, the frequency of API call of this child level agent will be higher compared to frequency of API call made by the root level agent. So you're saying that if we are placing the code for the agent, they will find agents.md at these respective levels. Exactly. In Cloud Code, however, you don't necessarily have to define this. The reason why I'm showing this to you is so that in case somebody is not planning to use Cloud Code for whatever reason, let's say your company is not allowing to use Cloud Code, but you want to construct agentic framework, because agents.md is universal. All LLMs understand what agents.md is. Cloud.md is, by the way, not universal. That you will have to explicitly define for the LLM, unless you are using Anthropic's models. But agents.md is a universal framework. So if you are defining it like this, then it knows that, okay, there are four sub-agents, four agents here, out of which two are child agents, one is a root agent, etc. What is the replacement for Cloud.md in Codex? I forgot the name. Codex I have been not used in the last many months. But however, if you refer to lecture number, I think 1 or 2, I had shown a table where you show the equivalent version of Cloud.md is shown for Codex. But at the end of the day, even if you are having the folder file name as Cloud.md, it is not an issue. If you explicitly mention to the agent that my system prompt level instructions are primarily mentioned in Cloud.md file, that if you explicitly mention, it will refer to it. If not, you have to use the default format. Yeah, in Copilot, it's called Copilot instructions.md. In many agents, there is a file called soul.md, S-O-U-L. So this is how it works. So if root agents.md is there, and in that, if there is one instruction, this will be taken. So use TypeScript, strict mode. Then inside of src folder, which is for web development, if there is an instruction like follow the coding standards in style.md, that will be taken. Then if there is a front-end specific agent inside the front-end folder, and if it mentions React, use React 19, no class components, it will be mentioned. And within the front-end, let's say you are building components like cards or modals or something, it will have its own sub-agent, and that sub-agent may have another instruction. Now, the context which this sub-agent will use will include this, plus this, plus this, plus this, provided there are no conflicts. There are no conflicting instructions. So what it may look like, the context may look like something like this. It will have all these four instructions embedded in the context. In the context of which agent? In the context of this child of child, or rather, yeah, sort of like child of child of child, because there are 4 levels of hierarchy here. So this is root, this is the coding agent, this is the front-end agent, and this is the component level agent. So this component level agent will have all these 4 instructions inside its context. Now, there is one question you may naturally have. I think one person had already asked this in 2 lectures back. What's the primary difference between Cloud.md and Agents.md? Cloud.md is the primary document which you will refer to for your system prompt. And this parts of Cloud.md will always be used irrespective of what API call you are making within that project, whether it's a sub-agent level API call, whether it's a root agent level API call, or whether it's not even a orchestrator API call. At all levels, system prompt, parts of Cloud.md, which are part of system prompt, will be used. Agents.md at the root level is used by the agent orchestrator, meaning there are tasks which are outside of the agent orchestrator's job. Maybe the Cloud.md, the Cloud Code has to utilize the agent orchestrator for making sure that the front-end agent, back-end agent, sub-agents, all of them are performing its task. But there may be other tasks which are outside of that, maybe to make sure that the overall folder structure is correct, maybe to make sure that the phases that are being implemented, which may include tasks which are not just web development tasks. Maybe there are other tasks for summarization or whatnot. For that, Claude.md will be always referred to. So Agents.md, please note, the orchestrator will be primarily using the agent. And under the orchestrator, there will be sub-agents. Under the sub-agents, there will be even lower level hierarchy agents. And all of them will refer to agents.md. And all of them will naturally will also get access to parts of Claude.md or entire Claude.md depending on the context. Why do I keep saying parts of Claude.md? Because sometimes Claude.md can be a huge file and you are not passing the entire file into the context. That will bloat the context. So you are using keyword matching or RAG. You will fetch only required parts from the Claude.md. Now I want to show you a few things, but before that, let me take you through some exercise and then we will come back to this. So I'll share a link with you. Just open this. Just a second. Okay, I just shared the link. I just want to make sure it's not shared in the waiting room. It's shared in the main. Yeah, it's shared in the main room only. Just open this and put your OpenAI or Gemini API key. Then, yeah, collab link also let me share in a moment. So collab is very long, by the way. So you will end up spending at least 30 minutes on collab. So I will share the collab and please use your API key from the environment. But for the exercise purpose today, I will be going through the interactive website. Yeah, so if we give a prompt saying build this particular component level feature, then automatically orchestrator will know which sub-agent to trigger. Because orchestrator, the role of the orchestrator is never to run the code or build things directly. It is to make sure that the people who are supposed to build is building. So I'll give you one more example of my recent workflow, which I have started. So for those of you who have not used Cloud Code or any agentic coding framework, know that often the execution will stop unless you very strongly explicitly suggest otherwise, and then it will ask you for your opinion. And sometimes you want to make sure that it's not blindly executing the task all the way. You want to give your opinion, you want to give your review comments and stuff like that. So one of the better workflows that I have recently tried and it's working very nicely is on top of Cloud Code, use OpenClaw. So OpenClaw is like a very nice assistant. So I will tell my OpenClaw to use a very cheap language model like Gemini 2.5 Flash or something like that. Oh, by the way, OpenClaw was so expensive. I tried it with 3.1 preview. It was like crazy level expense. Like for 10 minutes of my OpenClaw usage, I ended up, the bill ended up being like $7, $8 or something. It was like crazy. But if you use a cheaper model, Gemini, I mean, any model, by the way. So I switched down to cheaper model in Gemini. The expense was 100th or 150th, something like that. Then I will tell my OpenClaw personal agent as my assistant to take care of Cloud Code. So I told him OpenClaw Gemini should never be used for running any sort of experiment. So OpenClaw's only purpose is to be an orchestrator. Orchestrator for whom? Orchestrator so that it ensures that Cloud Code is building the project and Cloud Code is actually doing what it is supposed to do. So whatever output you have, make sure that OpenClaw checks the output Cloud Code produced, and if it's going in the wrong direction, course correct it. So there is a question, yes, is it safe to use OpenClaw? So what I did is, for my safety, I did not install it on my personal computer. I installed it on my EC2 instance. On EC2, there is no personal data, nothing. The only thing which OpenClaw is probably getting exposure to is my API key. But API key, I have pretty good control over. So there is no issue. Plus, I have not connected OpenClaw to any of my like calendar or Gmail or Slack or anything. I only connected it to my Telegram. And Telegram, I have never ever used to text anyone, like in the sense like I don't use it at all. So now I'm using Telegram as just a tool for communicating to OpenClaw. So on my phone right now, if I switch on Telegram, I can just text OpenClaw as if I'm texting, my personal assistant. Then OpenClaw will plan things accordingly, and it will ask Claude Code to execute the task. So my Gemini API will not experience a lot of cost accumulation, but rather Claude, which anyway I have a pro plan, there the price will accumulate. But yeah, please be be very careful with OpenClaw, especially with respect to price. Price is it's so expensive, especially if you are not careful with which model you use. You should see the number of tokens it accumulates. It's like for each conversation, after like 10 seconds worth of conversation, you will see that the number of tokens have bloated up. So something is wrong with OpenClaw. Maybe Cloud Code is not that terrible, but OpenClaw with respect to token consumption is so bad. At least from my experience, I don't know if it is universally true. So yeah, but that is a good workflow. That way, OpenClaw acts as if there is any issue, like let's say your session limit ran out on Cloud Code. How do you know? Cloud Code cannot tell you once the limit of token usage has ran out, it simply stops. But if OpenClaw is kind of supervising that work, it can automatically switch the account. It can take care of that. So, and it can notify me through Telegram if there is any issue in the execution. So I find that kind of workflow to be very fascinating, because everything is running on my EC2 instance. I can switch off my laptop and go home. And if any issue is there, I'll be notified on my phone on Telegram, and I can fix the issue. I can ask it to take the next step. Did you face any breaking point with OpenClaw, like context rot or forgotten memories? The thing is, OpenClaw's context is anyway very short. It's never executing anything. It's only orchestrating Claude Code's execution. So all the context that is loaded is into the Opus 4.6 context. Opus 4.6 context is anyway not managed by OpenClaw directly. It is managed by Claude Code. OpenClaw is only affecting the context that is there in my Gemini API. But Gemini's context is not that precious to me. I just need it so that orchestration can happen very nicely. Plus, if any issues happen, it can relay that information to me, and I can take some measures in a timely manner. Even if I don't have my laptop with me, I can do it. But the context rot, if at all it happens in OpenClaw, in Gemini, it's not so important to me, because first of all, I don't think it will happen, because the Gemini context window is big enough, and OpenClaw, if I'm using such that I don't pass any heavy tasks to it, I haven't noticed any issue in task breaking or anything like that. Yeah. So in my case, OpenClaw's work is very lightweight. It simply ensures that Cloud Code is keeping on working. It's never stopping or terminating, or if it's not detracking from its original task. Anyways, let's come back to this. So here I will show you a few examples based on LLM summarization, tool result clearing, priority trimming, and hierarchical compression. So let me show you first full transcript and what the situation is. The kind of hypothetical scenario is there is a ByteBridge company. That company is like a food delivery company, and there is some sort of rush on a particular day. There is a dinner rush where there are a lot of customers who are not receiving orders on time, etc. And we need to check the logs, check what has happened. And there is a ByteBridge API, ByteBridge AI chatbot also. So now if you look at the context, there are a lot of conversations that have happened, and there are a lot of tool results. So if I scroll down here, can you tell me which one resembles tool result? So order dashboard, this looks like a tool result, right? And as we discussed last time, tools, the way it looks like is the noun plus verb, or here maybe it should be a slightly different way. Order dashboard fetching or something like that should have been a better name, but whatever, does not matter. So this is one example of a structured tool result. Here is another one, driver analytics, the delivery person who is delivering. These are the analytics of that. Config audit, this is also the log of a particular tool result. Then this ByteBridge AI is basically the tokens consumed in the observation process or reasoning process of the AI model. Then these are user instructions, or operations manager Priya is sort of giving some sort of instruction. So in the full token that consume the context, it's like 1.9K tokens. And let's say for this time being, the token size, window size is 1.9K. Now, in LLM summarization, what we want to see is how many of key facts that are there in this is retained. So if there are 20 facts in this thing, in this whole context window, how much are retained when we do LLM summarization, and how much compression it results, right? So apply LLM summarization. So here an actual API call is being made to OpenAI. I gave OpenAI API key. And then OpenAI will, the GPT-4 or Mini, I think that's the model that I'm using, that will summarize. And let's look at the auto compaction result. So auto compaction result looks sort of like this. Sort of like this. And look at what has happened to the tool results especially. So one of the tool results was ByteBridge AI order dashboard. Do you see much about order dashboard here? There is not much about order dashboard at all, because those tool results are extremely compacted into natural language format. And from 1907 tokens, you went down to 257 tokens. And you can see that most of the parts here, ByteBridge AI is its own communications, or the summary of when the crisis began, which are present in these timestamps probably. All of those things are very nicely captured in this natural language, unstructured compaction, which can be later passed into the next API call. And what I have done here is I have asked the LLM also to separately capture the key 20 facts from this original document. So this original document is 1900 tokens long. From that, it has identified 20 facts, which ideally should be captured even after compaction. And then look at this, 18 facts are retained, 2 facts are not retained. So sort of like instruction retained ratio, IRR, is 18 out of 20, which is roughly 90%. But the compression is very, very effective. You went down from 1900 tokens to 257 tokens. Now, let me ask you a question. If I apply tool result clearing, what parts of this initial context do you think will be affected? Like, will order dashboard be affected? So order dashboard will definitely be affected. It's part of the tool result. Will, do you think this, let's say, operations manager Priya's conversation, do you think that will be affected by default? It will not be affected because it's not a tool result. So I will show you after implementing tool result, how the result looks before and after, and how many facts are retained. So tool result in this particular case has not resulted in significant compaction. Only roughly 550 tokens have been reduced. But that's also because out of my entire context right now, tool results are not overwhelmingly high. Tool results are consuming some number of tokens. And if you look at what has happened to tool results, so order dashboard, this tool result was roughly 200 to 300 tokens. And now look at it. It's roughly maybe 2 sentences, with each sentences having maybe 10 words. So it has been compressed to like 30, 40, maybe 50 tokens, right? So this order dashboard was very big, and that has been compressed so much. Similarly, there was one more section where there was another tool result, delivery metrics. See, this is again structured data coming from the result of tool results. And delivery metrics, again, you can see that will be compacted to just 2 or 3 sentences. But if you look at the other sections of the context, so what this operations manager Priya has mentioned, there is absolutely no change in this section because this is not a tool result. The ByteBridge AI's own communication, nothing has happened to it. So this is the advantage of tool result. And look at the facts that are retained. 100% of the facts are retained, 20 out of 20 facts. However, compression is only 1347. Compression happened to is 1347 tokens. So if you were to kind of score the technique based on retention rate versus score for compression, LLM scores better in compression because it has compressed to 200 tokens, 250 tokens, but the information retention rate is like a bit poor in LLM summarization. That's also because we are aggressively summarizing. We can also ask LLM to, pay more attention to key facts that we could have done. So can we combine tool results and LLM summaries? Yes, absolutely. So what you can do is, yeah, very good question. I really like the question. So that is exactly what we are seeing in the 80% threshold. So what is initially done is, initially do not summarize using LLM. Initially clear the tool results. Why is that? because tool results clearing is very non-risky. Because if you really want a tool result again, you can just call the tool again. Once the tool result is cleared, and let's say you did not compress good enough. So right now compression has happened only 1347 tokens. Then the remaining items you compress using an LLM, so that you are not immediately applying LLM compression. You see what happens to your compression after tool results are cleared. Maybe most of the facts will be still retained, but if compression is not good enough, only then apply an LLM summarization. Then priority trimming. So here, if you apply priority trimming, these are the 4 priority levels: P0, P1, P2, P3. So P3 is the routine conversation. You can see one P3 over here. So operation manager Priya has mentioned something like, great summary. I'll create tickets for all follow-up items, marking this incident as resolved. The driver distance spike was the key signal. So something which this manager has mentioned. It's a routine conversation which need not be retained. So this is entirely removed. And as a result, the number of tokens have reduced. And let's see what else has been removed. I don't think anything else is removed yet. How about tools? No, tool is kept. All of these are entirely kept. One thing I'm not so sure is 1686 tokens. So around 220-ish tokens have been removed. But was this Priya's conversation actually 220-ish tokens? I can see this to be 58 tokens, but it should ideally be 200 tokens. So yeah, there is another one here, 48 tokens. Then there is another one here, maybe 30 tokens. Yeah. So if you add up all the conversations this operations manager has made, yes, probably they will add up to roughly 200. So you can see that what the LLM has figured that is a very low impact or low risky thing to remove is all the conversations made by Priya, this operations manager. In fact, not all the conversations, some are kept. And then the total result is around 220 tokens being removed. Is the decision based on some kind of rule? It's based on rule. It's not based on semantics. Here it is purely rules. Tools have the lowest priority. Then even lower priority is routine items. Then if a task is being implemented at the moment, that will be at P1, and P0 will be system prompt. So here only P2 is removed, P1 is not removed. I think these tool results will come in P1. So yeah, so if more level of compaction is needed, next what will be removed is these tool results from P1. They will be removed. They will be trimmed aggressively. But here again, compression is very minimal. And because of that reason, it's not very surprising to see there is 100% fact or information retaining. This is not very surprising. Oh, I think I wanted to show you one more thing. Hierarchical compression, just to show you how the semantic based compression works. So this is hierarchical compression. And here what happens is, if something is in P0, the P0 will be found to be the 100% of whatever is there in P0 will be retained. If something is there in routine, P3, it's 0% retained. If something is in P2, 10% will be retained. And if something is 50%, if something is in P1, 50% is retained. So P1 is the tool results. So tool result will be summarized ideally. So here, this order dashboard, this is part of a tool result and it's compressed. Yeah, I will share the prompt that are passed into LLM. Yeah, I'll share with you guys. Right now, it is masked behind the this website front end. You mentioned it's earlier. Earlier, it's not necessary to use top model for compression. In Cloud Code, do you have to keep toggling the models for building any compression? Is this what you do typically? I personally have never explicitly mentioned the model to toggle between, explicitly mentioned the Cloud Code to toggle between the models. So I don't know internally what Cloud Code does, whether it switched to Haiku or Cloud Sonnet or something like that instead of Opus 4.6, because Opus 4.6 is the most expensive model, right, by far. So in the compaction, I am not 100% sure whether there is a switching of the model happening internally or not. Explicitly, I have never mentioned it, but I have to check it. I'll check and let you know. So this is how hierarchical compression runs. Again, P0 to P4, P3 levels are defined, but in each level, there is no complete trimming. Complete trimming may happen in P3, but if P3 is not removing everything entirely, P2 is not entirely trimmed away. P2 is kept 10%. 10% of P2 is kept. Yes, prompt should be there in Google Colab, yes, for sure. I just need to verify whether the prompts are exactly same in the website or Google Colab. That I have to check once, because I have made a few changes to the website recently. Then let's go into phase 2 just to see how all of this will appear visually. So here what we need to do is define a hard cutoff for when compaction is triggered and define a hard cutoff where the trimming is triggered. So can you tell me why do you need these two cutoffs? One is at 80% and one is at 95%. So if at 80% of the context window size, if compaction is already getting triggered, why do you need another emergency trimming of at 95%? What's the logic behind this? So the question is, why do you need two such thresholds at 80% and at 95%? So it can so happen that, let's say, first of all, after, let's say you are at the limit of 64%. And let's say you have 100,000 tokens in your token window. Now, 64,000 tokens are consumed. If the output of the LLM is another 30K tokens, directly your number of tokens will jump from, or let's say the output is not 30K, let's say the output is 20K. Let me just draw it here. So let's say this is 100K and you were here, for example, let's say at 50K. Now you call the LLM and LLM's output is 20K. Then LLM's output will fill this much more, sort of. Then you exceeded 80%, right? So maybe this will be at 85 or 90%, something like that. Then you will call compaction. And what is the first thing which you will compact? The first thing you will compact is probably tool results. And let's say your tool results are not that heavy. Your tool results are only occupying this much, right? So even after compaction, and even after compacting or even removing the tool results, you still are above 80%. Then what will you do? You will continue calling the LLM. And let's say in the next LLM call, your context window ended up filling up this much, where now this is 95%. So now what will happen is, this is an emergency situation because now you have barely any more tokens available to fill, which means your output LLM produces cannot fit in your context window. So now there is an aggressive trimming that happens where tool results are trimmed and P3 levels are trimmed, or even direct after tool results are trimmed, direct LLM summarization happens. And when direct LLM summarization happens, this thing will jump from 95 to roughly even 20 again. So I'll just let me erase all of this and let me show you visually how it will look like. This compaction, continuous compaction will look like. So just click this start simulation. So here you can see system prompt, user instructions, assistant instruction, which are maybe the sub agents, and then the tool, which are the results of tool call. And it keeps filling. The moment you reach, look at which part is getting trimmed the most aggressively. This purple part is getting trimmed or compacted the most aggressively, which are tool results. Tool results are compacted to very few tokens. Let me just play this once more by decreasing this compact at. So threshold I'm keeping to be 60%, and emergency, let's keep it at 95% only. Now, in first step, system prompt. Second step, user instructions. Third step, the assistant, maybe coding assistant, tool call. So tool call, there are results, okay? And then you get the results back. Then again, the assistant does something. Maybe it calls the tool. Then again, you get tool results. Then again, the tool results are passed to the assistant. Assistant consumes some token. Again, tool results. Maybe you inject a bit of user prompt here. So Priya has injected something. Then again, assistant works. tool call or maybe user instruction, then again tool call, again assistant, again tool call. So the moment tool call is increased beyond a certain point, not tool call, the entire context is increased beyond a certain point, compaction is triggered. And look at which part got triggered the most aggressively. This purple thing was compacted the most. Neither assistant nor user nor system prompt. System prompt is very rarely touched. See? So tool results are almost aggressively triggered. And we can also see one more thing. Let me put this at maybe 90% and emergency at 85%. Now what will happen according to you? There should be like a proper trimming that is happening. Let's see what all things are trimmed. So here actually one thing that may have happened in the logic is I don't see the entire tool result being removed. So in the backend logic, I have to make sure that entire tool result is removed. Right now, when you look at the difference between compact and emergency, it doesn't look like emergency is any different from compact. Emergency seems like it's also compacting the tool result. But ideally, emergency is supposed to, without any mercy, remove the tool results and remove anything else at P3 levels, P3, P2 levels. But right now, that does not seem to be happening. That's okay. In most of your usage cases, you will not come across this situation. You will most likely encounter the threshold where tool results are threshold 80% where tool results are bloating your context window. And the moment tool results are compacted along with the rest of the things, your context window will go back to maybe 36% or something like that. You might notice also in Cloud Code often when a new task is being implemented, Cloud Code will explicitly ask you, clear the context window and start execution. Sometimes it will ask you compact the context window and start execution. It itself will give you. And then in the recommended section, it will say recommended is clear the context window and start execution. Yeah, so P0, P1, P2. In this case, system prompt should be in P0 because that has the highest level of priority. P2 will be, P3 will be tool results because that is at the lowest level of hierarchy. Tool results which you already have available. You don't have to keep storing in context because in case if you ever need the tool result in the future, you can get it into the context window by calling the tool again. Then the assistants interaction and users interaction may or may not fall in P2 or P3 or P1 depending on the semantics, because sometimes the user instruction at that moment is very important. You should not be trimming it. Sometimes the latest interaction that assistant had is again important. So if I reset this back such that this is something like this and emergency is over here, and if you now keep looking at what happens to these colors, you will see that assistant's length is sometimes getting trimmed, but only after tool is getting trimmed. So tool has the lowest priority. So P0 is red color system. Purple color is definitely P3. The blue and green depends on what the context is right now. So there you will have to use some sort of semantics. And here, just look at this. The final tokens, final capacity of context window that has reached after this is 54%, meaning at the end of all of this, out of 2000 tokens, you are still at only 1087 tokens. On the other hand, if this trimming did not happen, by the time 28 messages are there between tool, system prompt, assistant, and user, you will definitely cross much above 2000. And here we are not really looking at how many key facts have been retained or anything. That we will not look at this in this exercise. One thing we should also look at is this multi-agent framework. So multi-agent framework, what we decided was for the same task, if there are different types of subtasks, multiple agents will be defined. So here this diff kind of file is showing you the difference between before creating a pull request and after creating a pull request. So plus is the new lines that are added, minus will be, plus is the new line added, minus is the new line or old line which is removed, just like when you make a pull request on GitHub. And here in this code file, there are three different things to take care of. And for that, three different agents can be utilized. One is the style of the code. So this will review the code style. What are the naming conventions for variables? Whether anything related to documentation needs to be looked at, and project coding standards. Security agent will scan for vulnerabilities in the actual code. Then performance agents will look at perhaps the execution speed of the code. So these three agents are there, and it has its own budget. And you can look at how the agent contract looks like. Okay, this is one topic which I did not discuss. This is where I exactly stopped. So coming to something like when you have two different agents, let's say there is one agent working on front end, another agent working on back end. There has to be some sort of commonality between between what the agents may produce. So if the agent working on backend is producing an output which is in a different format from what the front end agent is producing, there will be compatibility issues, right? So here there is a get request, get API /API /v1/user, here /API /users, and so on. So front end agent may have a default way of behaving because front end calls and front end schema is usually different from backend. So they may have a default behavior. But unless you explicitly say that the output you guys produce should be adhering to certain format or certain structured format, you will not be able to integrate them. So there is an idea called contract first pattern. So contract simply means the orchestrator will define a schema which both of the agents should sort of follow. So if there is an API called related schema, API specifications.json file will be defined by the orchestrator. By the way, Claude Code does this automatically. You don't have to say explicitly that when you are spinning subagents, define sort of like the contract that these subagents should follow. You don't have to explicitly say that. It is implicit. However, if you are building your own coding agent outside of Codex or outside of Claude Code, this is something which you will have to define explicitly. You will have to tell the orchestrator that make sure that sub agents are following or building based on a certain predefined contract, so that when those two things are integrated, they will actually work. An example of this is I had talked to you about building my news aggregator agent, or even building a central brain for Visuara. So the central brain for Visuara is an agent orchestrator. And then there are many sub agents that we are building. Now, one schema that we are now forcing these agents to follow is a schema that will allow us to have a two-way MCP. So two-way MCP as in, it's not like one part can be client and one part can be server. It can switch the roles. So both ways it can act. And for this to happen, we had to explicitly mention it in the system prompt agents.md that the output that is produced by this should follow the MCP format, which are mentioned in the guidelines of my central orchestrating agents. Output of my email agent should follow the format mentioned by this agent. And same thing, when Visuara is acting as the client and this agent is acting as the server, there is a specific way of communication from this client to the server. So this was again an explicit instruction, not implicit. The reason why this had to be explicit is because we only defined the MCP ourselves, which means there is a certain structure that these sub-agents should follow. So that is what this section is about. Let me go back to the this section. So the style agent has its own input schema and output schema. Security agent contract defines its input schema and output schema, and so on. And when you run the multi-agent, this is just a simulation, by the way. When the multi-agent schema is run, the orchestrator will decide when to call the style agent, when to call security agent, when to call performance agent. Each agent, the token consumption is completely different, needless to say. All right. So this is just to visually show you how it will work. I want to show you a couple more things before we move on to the agents.md file structure. Okay, to this I will come last. I want to show you one more thing. Yeah. So the way in which sub-agents will communicate. So let's discuss a little bit about that. So there is a concept called fan in and fan out. So fan in, fan out is nothing but how does a fan work? If a fan is rotating, if something is released from the fan, things will go outside, right? I mean, it'll be in straight line, but it'll go outside in this way, right? So fan out is the idea where the central orchestrator will spin isolated agents, which have, and these agents have nothing to do with each other. Okay. And they barely share any, apart from system prompts, they don't share any base documents or anything like that. So this idea is in general called as fan out. But however, sometimes orchestrator can say, apart from system prompts, there are a few more things which I want to share with the agents. So a good way to visualize that is in this way. So this is the orchestrator. This is sub-agent number 1, sub-agent number 2, and sub-agent number 3. By default, the system prompt is passed directly to all the 3 sub-agents. So this is system prompt to agent number 1, sub-agent number 1. This is system prompt to sub-agent number 2. This is system prompt to sub-agent number 3. Anything else, let's say if there is a config audit which needs to be shared between all the agents, or if some other file needs to be shared across all the 3 agents, that is decided by the context curator. So now config audit may be, so these 2 green color lines show that config audit is shared between root cause analyst and remediation planner. So this file agent, the orchestrator has decided that these 2 files are sort of like base documents, shared base documents for sub-agent 1 and 3. And this is system prompt. The remaining file will completely depend on, the sharing of remaining files will completely depend on what the orchestrator seems fit to each sub-agent based on the sub-agent's task or sub-agent's talent, what it is supposed to do. So maybe architecture diagram, orchestrator will decide that it needs to be only shared with impact assessor. So impact assessor will now get access to system prompt. It may get access to metrics dashboard or error logs, and it will also get access to architecture diagram. So this is how the custom context is set up for each of the sub-agents separately. Now, if I go back, this full isolation is the idea where every single sub-agent is having completely different inputs into the context. So there will be some base instructions. This base instruction can be in the form of Agents.md. Here we are not mentioning the Cloud.md file, that is implicit. I don't have to mention it. But let's say there are 3 agents, one for triage, one for root cause analysis, one for recovery, for whatever event that has happened for this food delivery company. Now, the things which will go into the context of triage is its own base, meaning its own agents.md file, which is not shared. So please don't get confused. This is base with 200 tokens. This is base with 200 tokens, but this is different from this. This is the agents.md file for the triage agent. This is the agents.md file for root cause, and this is agents.md for recovery. Then there will be other documents, which are other documents or other tokens which are passed into the context, which are relevant to those agents. And these are fully isolated agents. And in this case, for example, okay, let me show you 3 agents, then I'll ask you the question. Then there is another concept called shared base. So shared base, visually, you can see like this. So agent 4, 5, and 6, in this case, this green color shows that there is a common base that is shared between these 3 agents, meaning common documents, which the orchestrator decided to give. But apart from that, there are completely different agent level knowledge which is passed into the context. So security agent will just get information, will get, in addition to the shared base, will get information regarding security. Performance agent will get information regarding performance, and so does style. So this is the idea of shared base plus whatever is isolated between the agents. The last one is sequential subagents, where the input that goes into agent number B will depend also on the output coming from agent A. So this is sequential because unless agent A is fully implemented, agent B cannot work. A good example of this is, for example, let's say we are working on a research agent, and the implementation can happen only after literature review is done. Then literature review agent A may come only before agent B, and agent B can work only after literature review and gap identification is done. It cannot work before. So this is sequential pipeline. Now let's go back here and just look at shared base context, how it look like. So here, this is the shared context between the three: triage agent, root cause agent, and recovery. There is a common shared base. Then apart from that, there is agent-specific instructions, and this will consume certain set of tokens. In sequential pipeline, the triage agent's output is summarized and passed into root cause. So in root cause, you will see there is the triage agent's findings. Then that findings plus findings from the root cause agent will be passed into the recovery agent. So recovery agent now has in the context summary from triage agent plus summary from whatever root cause agent has found. So recovery agent cannot function without these two things that are passed into the context. That's the reason why it's called sequential. How the pattern defined, how is it defined sequential and parallel? It is implicitly defined by the agent orchestrator itself. To give you a simple example, when you are, think about it, if you are building a website dashboard, you cannot run a components agent, or you cannot run an agents.md corresponding to the components before you, let's say, fix the overall architecture of your website. So if the folder structure looks something like this, MD, and then the root level agents.md. And here you have the coding agent. So this is another agents.md. Then here you have front end. And within the front end, you have components. And this front end agent might have said a few things in the component. In the component hierarchy, maybe there is a navigation bar. Then inside navigation bar, let's say there are buttons. Okay. Now, if there are agents for creating buttons, agents for creating navbar, agents for creating separate components, etc., the agents.md corresponding to this button section cannot run before agents.md corresponding to navbar has executed. Because agents.md corresponding to navbar says that, hey, we are currently building navbar in which 3 buttons are required: dashboard, login, logout, something else, home button. Only then the agents.md corresponding to this will execute. So here, the hierarchy of this folder structure is kind of implicitly giving the agents.md in the root an idea which agents will be executed at what time. But sometimes some things can be in parallel, because when you are building the navbar, you could also build your hero section. You could also build something else in your page. And while you are building the front end, you could also build some parts of the back end, right? So if you were to manually define in sequence which agent comes first and which agent comes next, I think it will cause more confusion to the model than bringing some sort of clarity. What is better is create a very nice folder structure in which the agents.md itself implicitly defines what the order in which the sub-agents are executed. If we have agents.md on top, what is the need for cloud.md? So cloud.md, so agents.md is only looking at maybe coding task and testing tasks. So let's say there are 2 tasks, coding and testing. But let's say at the project level, you have many other things to do apart from building website. Maybe you have to plan project roadmap, PRP, project roadmap planning. Maybe you have to assign tasks to your team members or something like that. Like once this is done, you have to, let's say, push something to Trello or Kanban, or you have to check the details of your project execution by the rest of your team members on GitHub. So at the central level, there are many other tasks which cloud.md can do, which let's say an orchestrator agent for coding cannot do, or orchestrator agent for coding plus testing cannot do. So agents.md is specific to what all tasks it is supposed to orchestrate. Cloud.md is specific to everything that your entire project in your workspace is supposed to do. So Cloud.md will be corresponding to your workspace. And then sometimes, so this agents.md, it might be confusing to you because right now I have shown you just one agents.md in the root file, right? The easiest way to remove this confusion is I can literally move this out of my root. So I'll move it here. And I will say that I don't have any agents.md at the root level. My two agents.md is one agents.md is at the coding level. Then I may have another agents.md at the maybe project roadmap planning level. And at the root level, there is no agents.md. But at the root level, I will still have cloud.md. So whether you have an agents.md at root level or not, it's up to your project specification. But at the root level, you will always have a cloud.md file if you are working in Cloud Code. Okay, let's get back. So this is how the sequential pipeline will look like. Now just answer the simple question. There is a scenario, multi-domain restaurant onboarding. 3 specialist agents are needed to verify a new restaurant joining the platform. In this case, just read this and just tell me what type of agent would you do? Would you use full isolation, shared base context, or sequential pipeline? So there are 3 agents. They have to do few things. They are analyzing at the end of the day, it's the same restaurant. Same restaurant application data. Each agent applies domain specific expertise. So probably there has to be a shared base is what I'm thinking. Let's see. So there has to be a shared base, but there will be fan out. Fan out meaning there will be isolated context also. How about third scenario? Let's come back to second scenario after this. Parallel city expansion analysis. 3 agents each research a different aspect of potential new cities for expansion of your food delivery platform. Demand agent queries food ordering trends. Then completion agent maps this. Logistics agent delivers, evaluates the driver availability. So if it's a parallel city expansion analysis, it's a completely different city. And maybe the things that you need to do in one city and the other city are completely different, which means there is nothing to share, right? So it could be full fan out, like full isolation. Then the last thing is rush hour incident response. An active Friday rush hour crisis needs urgent resolution. First is triage incident identifies the severity of the incident. Root cause agent uses triage to find findings to pinpoint to the. So basically here itself, it says triage findings are needed for root cause agent to analyze the issue. And then the recovery agent uses both the triage results and the results from the root cause agent, which means it looks like a sequential pipeline because the output of one depends on the input of one depends on the output from the other. Then let me show you one more thing. This Windows, this part will be very interesting. So again, look at this folder structure. So this will answer some of the questions which you may have. Your workspace is ByteBridge incident. Okay, this is your project workspace in which there is cloud.md, but there is no agents.md. But inside the folder, inside this agents folder, you have an agents.md. Now this will be the orchestrator. Now inside this orchestrator, inside this agents folder, there are 3 subfolders, one for root cause analysis, one for impact assessment, one for recovery planning. It has its own agents. Now let's just run a simulation of how this looks like, which files will be passed into which agent. So orchestrator will have access to system prompt. System prompt says you are a specialist agent in ByteBridge incident response team, follow this thing, respond in JSON format and so on. Cloud.md has bunch of things about the team, incident response conventions, terminology, etc. Then incident briefing document. Incident brief is this document is probably passed into this working directory directly because this ByteBridge incident is the folder to which some briefing might be there. So this incident briefing.md, you can imagine to be similar to the ideas v2.md or something which I discussed a few lectures ago, like a markdown document which kind of describes what the situation is. And Cloud.md will be independent of all of this. Cloud.md will take care of all the incidents broadly. Incident briefing.md will describe the specific incident that has occurred. And then there will be instructions provided to orchestrator. So orchestrator instructions are provided in the agents.md, this one, and orchestrator's delegation plan. So now this delegation plan will be a separate file, which is not shown here, but what that file will decide is what agents, what sub agents now to run. So orchestrator will decide in the first step, I need to run root cause analyst agent. So send the config audit plus driver analytics to root cause agent. Then after the root cause agent output is available, impact assessment. So for that, I need the impact assessing agent, to which I need to send the root cause summary, right? After that, have the recovery planner and then synthesize. So let me just run one step and see how the step proceeds. So the first step is root cause agent is called because in the orchestrator's delegation plan, first sub agent that is called is root cause analyst. So root cause analyst is also getting system prompt. So it's the same system prompt. It's also getting access to Cloud.md, the same Cloud.md. It's also getting access to incident briefing. Incident briefing is that markdown file at the root level. So this is getting accessible to root cause analyst. Apart from this, root cause analyst will have its own instruction in its own MD file, agents.md file. So it will say your role is to act as a root cause analyst, then analysis of the current incidents, and then the config audit trail and driver analytics snapshot is something which orchestrator ended up deciding to send. So orchestrator had sent config audit, send driver analysis or analytics. So these two things orchestrator decided to add into the context of root cause analyst agent, and which contributed to 150 tokens, 160 tokens. So totally 310 tokens. These 310 tokens came here because orchestrator decided to add it. This 100 tokens came because it is part of the agents.md file, this root cause analyst instruction. This 85 plus 140 plus 135 tokens came because it is part of there is a shared base plus system prompt is anyway part of the all the agents. So incident briefing is sort of the shared base. It's shared between all the agents. And now when we run, now root cause analyst agent has executed. Its result are passed back as summary into the orchestrator. So now orchestrator has an additional 180 tokens. Ideally, these 180 tokens, some output tokens will be stored in the root cause analyst also. It's not being shown here. So please don't get confused because root cause analyst is calling its own API. That API will have its own results. Those results will be stored in this context window only. So the 770 should ideally increase to something. But then whatever the output is, the output can be summarized and will be stored in the orchestrator like this. Now, what is the next step? Next step is orchestrator already has a delegation plan. It has step 2 is impact assessor agent. So in the next step, orchestrator will call the impact assessor, which will get access to the same 3 files, system prompt, cloud.md and incident briefing.md. But there are now new files. This new file is the agents.md corresponding to impact assessor. This new file, root cause summary, is the result of the previous agent's execution, which is the same thing. This same 180 tokens are here. Then this order pipeline metrics and normal performance baseline was added by the orchestrator. So orchestrator had said, send root cause summary plus order metrics plus baseline into the impact assessor agent. So these two files of 130 tokens and 90 tokens came to the context of impact assessor because orchestrator had planned it. So total 870 tokens. Now impact assessor will run its step, which will produce its output. And that output is now stored as a new set of tokens in the orchestrator's context. So those new set of tokens are now 165 tokens. Now the third and last step should be orchestrator plan is called the recovery planner, to which these two things are sent along with some playbooks. So in the next step, recovery planner will get access to system prompt, cloud.md and incident briefing. Then this new file in yellow color is the recovery planner instructions in the form of agents.md. These two green color ones are the summary of the implementation of the previous two agents. And these two files, recovery metrics and customer recovery playbook, were passed by the delegation by the orchestrator when it delegated the task to recovery planner. And then finally, recovery planner's final summary will be over here. Recovery plan, immediately activate tier 2 and 3 refunds for all the affected orders, 24-hour push notification, so and so and so. And that's it. I think that's the last step. Yeah. So look at how the orchestrator, how many times it interacted. Orchestrator's context got filled after 3 interactions, 1 interaction with each agents, right? And finally, only the output that we need. I mean, the recovery plan, because this whole workspace is about when you have an incident, how do you recover from that incident? Incident could be large number of orders not getting delivered or whatever. So this is a brief overview of how it looks. And you can also see this here, how the context is getting full. So Cloud.md plus briefing is the 360 tokens that are part of all the or agents, orchestrator, as well as the 3 sub agents, Cloud.md plus briefing, Cloud.md plus briefing. Then this 205 tokens are contributed from Agents.md of orchestrator, but then orchestrator will pass the config file plus audit. Those are the 310 tokens. This 100 tokens are in the Agents.md. So this yellow color defines the Agents.md file, number of tokens in the Agents.md file. And these are these files, these 3. This Agents.md, this Agents.md, and this Agents.md, 105-ish tokens each. 100, 110, and 105 tokens each. This one is the orchestrator agent, which has around 205 tokens. All right. So this is roughly how it looks. Now, what we can do is, I think there was one section which I wanted to show you. This I already, yeah. I think this will be covered anyways in the quiz part. Basically, what we need to do is, there are 3 sub-agents. So one sub-agent will take care of order-related items. One sub-agent will take care of delivery-related items into the items, meaning delivery-related data into the context. One agent will take customer-related data into the context. And each agents we have defined to have a context limit, 950 tokens, 900 tokens, and 1100 tokens. And these are apart from the system prompt and apart from the task briefing.md, which are already passed into all the 3 agents. You have these many these many 1, 2, 3, around 10 or 12 items to be passed into the sub agents. The question is, how would you decide that? So we don't have to spend time on this, but I will just show you the solution. We can spend time in the quiz part. So the solution is that you decide the context to be passed into the each agent based on what that agent's capability is. If one agent is really good at handling things related to order, pass things related to order to that agent's context. If another agent is supposed to handle things related to customer, pass only things related to that into the particular agent's context. Now let's go through a few questions that will make things a lot more first confusing and a lot more clear afterwards. Please answer your options in the chat. Some questions are actually very, very straightforward. So I'm expecting all of you to give the correct answer. What is this information retention ratio? Fairly straightforward. What exactly is the definition of information retention ratio in context compression? Obviously, it is the ratio of what are the total number of facts existing in the document compared against the total number of facts that were preserved after compression happened, right? So ratio of key facts preserved to total key facts after compression. Fairly straightforward. What about this? Which compression is most effective for large conversations with large embedded tool results? Fairly straightforward. There is nothing confusing here. Do you do LLM summarization or would you do tool result clearing? Probably these are the only 2 options coming to your mind, right? So the most effective one for large tool results, if tool results are definitely your biggest item which is consuming your context, tool result clearing should be the easiest one. But if tool results are equally proportional to other items in the context, maybe then you will first do tool result clearing and then do LLM summarization. So LLM summarization can result in a lot of loss of information also. A 15-turn operations debug session has 5,000 tokens. After LLM summarization, it is 400 tokens with 16 out of 20 key facts retained. What's the IRR? I mean, fairly trivial. 16 out of 20 means you multiply by 5. 16 multiplied by 10 is 160. Multiplied by 5 means it's 80. So 80% should be the IRR. Fairly straightforward. In hierarchical compression tiers, like critical 100% retention, important 50% retention, and so on. What determines which tier a message belongs to? This is one question many of you might have doubt about. So here the question is it D or C? That's the question. In hierarchical compression, do we decide the hierarchy based on some rules or based on LLM? Based on semantics. So in hierarchical compression, it should be based on semantics. But in trimming, it's based on, it's completely trimming, it's based on rules, right? But here it's based on semantics. Then why is priority trimming considered riskier than tool result clearing? What is the risk behind priority trimming? So this is a little bit confusing, right? Just think about it. I think people are typically, generally confused between B and D. Okay, first of all, let's eliminate. Priority trimming requires more compute power to execute than clearing. There is nothing like that. So A, we can eliminate for sure. Priority trimming can only done by an LLM, while tool clearing is rule-based and deterministic. Actually, priority trimming can, trimming can be done by a non-LLM, because in priority trimming, hierarchy is defined based on P0, P1, P2, P3. P1, P3 is the tool results and maybe earlier conversation history, which we can define based on rule. P2 might be things which are earlier in the later part of the conversation, like conversation that just happened recently. So we can define some rules. So here, necessary LLM is not really required. Tool result clearing uh, uh, Tool result clearing preserves reasoning context while trimming removes entire messages that may not be implicit. Tool results are always redundant, so clearing them is safe, while user messages always contain unique information. Let's go with one of them and let's see. So answer is B. Tool result clearing preserves reasoning context, but these two are very confusing, right? They pretty much almost feel like they are saying the similar thing. But tool result clearing preserves the reasoning context, while trimming removes entire message that may contain implicit dependency. Tool results are always redundant, so clearing them is safe, while user message always contain. Maybe the always word is not so true. It's not like always tool results are redundant. We can't say. And always user message is unique information also we cannot say. If this was reworded in a slightly different way, it would have been even more confusing whether B or D is correct, right? So maybe this always word is not the right thing to say. An operations transcript has 3 tool results averaging 250 tokens each. So 750 tokens. In B, it is saying, let me go back to fifth. Tool clearing preserves reasoning context, while trimming removes entire messages that may contain implicit. So basically, in tool result clearing, if you remember, LLMs can also clear tool results sometimes in the LLM summarization, but there it's not clearing the tool results, it's summarizing in 1 or 2 sentences. If it is complete tool result clearing, it is not LLM based, but in LLM based summarization, it can clear. In LLM based summarization also, tool results are cleared technically, right? Tool results are summarized into 1 or 2 sentences. But yeah, what this is saying is tool result clearing preserves reasoning context, while trimming removes entire messages that may contain implicit dependencies. So trimming means, in trimming, what may come in your P3 level can be tool results as well as your conversation history. So your conversation history, which is far from the most recent conversations, may get cleared. So it may affect the context. Conversation history or user inputs which are far away from the current user input may again get removed. That may affect the context. That is what this is saying. Okay, you have 3 tool results, each averaging 250 tokens. Then 12 conversational messages averaging 60 tokens each. So this is 12 multiplied by 60, which is what, 720, and this is 750. If you apply tool result clearing, replacing each tool result with a 30 token summary, what is the approximate compression ratio? It's fairly easy. You can So basically tool results were originally 3 multiplied by 250, which was 750. Now tool result becomes 3 multiplied by 30, which is 90. So your tool results go from 750 to 90. So whatever that number is, that much compression is there. So about 78% of original tool result drop from 750 to 90 tokens. Let me check if first of all, yeah, this is not definitely 55%. This is 90 out of 750 is closer to 78%. Then in a 3-pass auto compaction system, why does tool result clearing happen before message summarization? This I think should be clear. We have discussed this in detail. Like, why is tool result clearing the first thing which you do in auto compaction? The reason is, as we discussed, tool results are kind of deterministic. Of course, depends on the tool, but in general, when you call the tools with a certain condition, it will always give you the same output. So tool results are sort of deterministic. It's low risk because if you ever need it again, you can simply call the tool again. So you can get maximum compression before resorting to LLM-based summarization, which can be lossy. You saw that in the example which we discussed in the LLM-based summarization, that was the most lossy summarization because 18 out of 20 facts were retained, 2 did not get retained. What is the recommended compact at threshold for production auto compact systems? This we have discussed fairly straightforward. You should know this. So there is compacted and there is emergency trimming, right? So compacted is typically 80%, trimming, emergency trimming at around 95%. Then what does context rot refer to? I think by now this is the only thing, maybe you should be able to answer this in the sleep. It's basically degradation of models, context over time and usage. Then during an auto compaction simulation, this question, auto compaction simulation, pass one fires, which is tool clearing fires, but the context is still at 88% capacity. Emergency threshold is 95%. What should happen next? First of all, is everyone clear why after tool clearing the context is still 88% capacity? Why is it not coming below 80%? Is everyone clear why? Because auto compaction triggers at 80%. If so, my question is, if it gets triggered at 80%, how come the capacity is still 88%? Wouldn't it bring it below 80% anyways? Why is this sensible? I'm just trying to recollect your memory. Why is even after auto compaction triggering, why does it stay at 88%? Simply because in the whole context, you don't know how much is the tool output. So when you clear the tool or compact the tool results, there is no guarantee that you may go from 94% to 79% or 88%. You might still stay at 88% or above 80%. So what happens? So what should happen now? Let me just check your answers. B, A, B, B. Most of you are saying B. Some of you are saying A. Okay, I'm not sure which one you're saying. What should be the next step? So nothing is between 88% compacted and emergency. So system waits for more messages. Is it that, or system retries pass one with more aggressive tool clearing? Okay, all of you are, it seems like many of you are saying A, some people are saying pass one, retry pass one. So what should happen is, there are different levels of clearing. First of all, in hierarchical clearing, first level of clearing is tools. And second level of clearing is let's say some things in P2 or some other things apart from tools in P3, which is like conversations that are very old, or user instructions, user prompts that are very, very old. Maybe you can clear that because rest of the things about user instructions are already captured in the rest of the context. So something should trigger, right? That's what ideally should happen, because if we don't do anything, we are guaranteed to reach this emergency threshold. You know when emergency threshold is used? Emergency threshold is used only when, imagine that your context window is right now at 79%. At 79%, there is no compaction. Okay. Now let's say your LLM produces an output, and that output is these many tokens, such that you jump directly from 79 to, let's say, 96%. At that point, auto compaction, which happens at 80%, will not get triggered. At that point, directly emergency threshold will get triggered. But anything before that, if auto compaction is not able, the pass one of tool clearing of auto compaction is not able to do anything, it will try pass two. So that is the next logical step should happen. If nothing being done is not a good thing, because then you are anyway, see, at 95% anyway, you are trimming without any care, because your context window is almost dead. So you have to trim. So there is no choice. But at 88%, you may have some choice to remove P4 and P3 only. Do not touch P2, right? So when you have more choices, you will execute that choice. So it should be firing pass 2 immediately. Pass 2 is compact at, run the compact at, but for maybe the next level of hierarchy. Okay, another one. Why is the emergency threshold, emergency at, is separate from compact? Why do we need these two things? So why do we need this? It's very aggressive. So emergency threshold compaction, trimming is very aggressive. It will literally remove entire portions, whereas compaction can be made using LLM. So if LLM compacts something from tool results, it can still compact whatever is remaining. But emergency trimming may completely remove tool results, so nothing will be available. Plus, it will remove anything else needed. In multi-agent code review system, why is contract first design critical? First of all, remember what is contract first. Why is it needed? So contract simply means defining a common schema for all the agents so that the results can be merged or combined together to build one single product. So if you have sub agent for front end, sub agent for back end, whatever they produce should be compatible with each other. Then what is the main advantage of fan out or fan in? So fan in simply means you have multiple sub agents, you compile their results into one single orchestrator. So why is this preferred over a single agent approach for code review? So I think this is a bit confusing, right? Okay, let's first of all look at what may not be the answer. Fan out is always faster because agent run in parallel. Uh, Not sure. It need not be fast. It depends on the particular project. So it's probably not A, right? Fan out uses fewer total tokens because the difference is split into smaller pieces. There is no guarantee of that. It may even end up using a slightly more tokens. Why? Because the system prompt is passed to all the individual agents. So maybe the total number of tokens consumed may be a bit higher. What about a D? Multiple agents can use different LLM providers simultaneously, reducing vendor lock-in. I mean, for sure, that is possible. For sure, you could do that, but that's not primarily the reason why we use fan out. The reason is you have specialist agents. Some agent is good at code review, some agent is good at security issues, some agent is good at perhaps testing. So you need the specialist to invoke their special skills. In a multi-agent system, the orchestrator sends the full PR, pull request diff, to all the three sub-agents. What's wrong with this? So earlier we saw the example where the PR diff was sent such that only the required parts were sent to the specialist agents. But what if we send the whole thing to all the three sub agents? What's wrong with it? Okay, first of all, let's think about it. Nothing wrong? No, it's not like there is nothing wrong. There is something wrong about it. So it's definitely not A. It violates the fan out pattern, which requires equal sized input to all agents. There is no such rule. We don't need equal size rule or anything. How about B and D? B versus D. It wastes tokens. Each agent should receive only receive the code sections relevant to its domain. That's the first thing. B. D is it causes agents to produce duplicate findings since they all see the same code. Is D true? See, D is not true. Just because all agents receive the same input does not mean they all will produce the same output, because their capabilities are different. Maybe these agents have different access to different tools, right? So there is no guarantee that they will all produce the same findings. But if the entire code is provided to sub-agents, the sub-agents can definitely see the relevant sections of the code corresponding to their expertise, and they can produce the findings which they are supposed to find. But the thing is, it will also receive a lot of tokens which it cannot do anything with, because if there is a, let's say, a agent which can do some testing on a function, maybe a code review agent looking for schematic of the code need not receive those tokens. So it wastes tokens basically. But there is no guarantee that providing the same input to all agents will provide the same output. There is no guarantee. Different agents have access to different tools. Then a security agent finds 5 critical SQL injection vulnerabilities, but its output schema only allows the maximum severity warning of maximum severity of warning. What design principle was violated? So output schema is not allowing it to produce an output which it's supposed to produce because of its restrictive nature. So that's the reason why it will not. This is not a good structure. What is the orchestrator's role in the fan-in phase of multi-agent code review? So fan out we discussed. From orchestrator you go to different agents. Fan-in is the opposite of that. So what is the role of orchestrator? So this is where the deduplication idea comes. So earlier we discussed, if we pass the same input to 3 agents, they all will produce the same output. They will not all produce the same output, but maybe some findings may be duplicated between the agents, because maybe 2 agents have similar, some capabilities of 2 agents might be similar. Maybe then because of that, they can produce same findings. So those findings we deduplicate, and then merge the finding from all the agents and determine overall review verdict. So this central orchestrator agent basically collates the information coming from all the different agents. So in the WSCI framework, what does the C specifically address? Very trivial question. So it basically compresses, reduces what is already there in the context window while preserving critical information. So compress is basically compressing what is there in the context window already. Okay, this we have not discussed, so I will move to this. What is the relationship between compress and isolate in the WSCI framework? Fairly straightforward, nothing confusing at all. Compress will reduce the context within a single window. Isolate is like multi-agent framework. It will distribute the context so that different agents can have its own API calls. So they can work in different context windows. Then in the context pyramid, which layer has the highest preservation priority during compression? This also we have discussed many times, but which one has the highest priority? System instructions and persona, they define the agent's behavior and must never be removed. A production agent handles 50 turn customer support conversations. After 30 turns, the responses become increasingly confused and contradictory. What is the most likely cause? You know this already. It's the context rot. On Visuara's website now we have a calling agent. I urge you guys to try it if you really want to. Just go to our landing page, and there is like a phone icon. Sometimes it'll say like daily limit has reached, but basically you can just there is this ask AI option. So here what we have done is we have an agent with a specific context about our programs and stuff like that. And you will notice that after like 5 minutes or 6 minutes, its ability to communicate in a very nice way will significantly reduce, because we have not optimized the context or anything over there. And after some point, it will completely disconnect. So basically its context window will become full. So compaction and compression we have not yet implemented. So you will see a classic case of context rot if you just look at our current chatbot. But I think now we are making some implementations. Not sure if we have pushed it to production yet, but that was the case 3 days back. Then so here context rot will happen. Then your multi-agent system occasionally produces duplicate findings. The style agent and security agent both flag the same missing authentication decorator. How should you handle this? This we already discussed 3 questions ago in multi-agent framework. So think about this. Sometimes sub-agents can give findings which are duplicate. The only place where you can analyze this is sort of in the orchestrator, because these findings are directly going into the orchestrator. So in orchestrator, there should be a deduplication step, so that these similar findings are grouped, so that the context window is not unnecessarily bloated. You are designing an auto compaction system for a coding assistant. Which type of message should never be compressed or removed? Okay, this is an interesting question. So what should never be compressed? This we briefly discussed during the lecture also, if you remember, right? So if you read the structure, okay, let's read this. D, the user's initial request that started the conversation, it's already captured in the ongoing context. So user's initial request, okay, after the initial instructions, when you are building something, what you are building, why you are building, for what you are building, for what's the reason why you are building, all those things are kind of captured in the context. Although if it is part of Cloud.md file, we should not delete the file directly, right? But if there are some initial instructions, it kind of is there in the context already. So if the very initial thing is removed, it's kind of okay. But look at this option A, the most recent code edit the assistant proposed that the user hasn't yet accepted or rejected. So when you use a code editing assistant, you will see that the diff is shown in the whichever IDE you use, right? And that diff you have to either accept or reject before moving to the next step. So if user has not gotten a chance to say whether I accept this change or reject this change, probably you should not delete that from the context yet, right? So you should keep this. This is like a very special case, right? So this is a special case where you should not be removing this. Then a multi-agent system for food delivery crisis has agents for order flow, dispatch, driver dispatch, customer support, and communications. The communications agent need access to findings from all other agents to draft the status update. How will this be architected? In what way this will be running? Give the communications agent access to full context window of all other agents. Include the communications agents in the initial fan out so it can observe the investigation in real time. Run communication after the others are complete and pass only the structured output. Then have each agent send their raw context to shared database. So this is classic example which we discussed earlier. If there are agents whose input depends on the other agent, it's like in a sequential way, right? Of course, sequential agents will also get other things in the context. They will get Cloud.md or other markdown files which are relevant. So there will be a shared base also, but the agent specific summary will be happening in sequence. When Cloud Code spans a sub-agent, how does the sub-agent receive its context? It shares the parent's context window via memory map IPC. It inherits full parent conversation history automatically. It receives a separate API call with a curated prompt containing only relevant context. It reads from a shared database that both parent and sub-agent can access. It's not like that. The relevant context is curated by the orchestrator. Here, the orchestrator is Cloud Code. So this sub-agent will have its own way to call separate LLM. I mean, its own ability to call Claude, whichever model you are using its own API. An orchestrator sends the entire 50,000 token conversation history to its 3 of the sub-agents. What is the primary problem? This is again clear. The primary problem is context rot of each subagent. So the whole point of creating the subagent itself is lost here if you are sending the same humongous 50,000 token history into these agents. So very, very straightforward. In the shared base context pattern, what is the base that all agents receive? So there is one minor issue in the wording here. I mean, answer should be B because a common foundation plus agent specialized context. So agent specialized context, which is agents.md, it is special to itself. Okay, by the way. So in this, from this option, maybe we should just delete whatever is written after this plus. Of course, it is plus something, but the common foundation will be system prompt, task description, and shared data, like in the food delivery incident report.md, cloud.md, and any other shared data. So that will be forming the common base. Then why does the sequential pipeline pattern produce higher quality findings than full isolation? So there is one point which I want to discuss here, which is, see, sequential pattern, pipeline pattern, it's like a double-edged sword, because for reasoning, it can do better job because you can validate what one agent has done using another agent. But at the same time, it can also cause error propagation. If one agent produces something erroneous, it is propagated to next agents also, right? So it's like a double-edged sword. So you will have to put some guardrails. Three agents have 1,000 token budget. The shared base is 300 tokens, and each agent needs 600 tokens of specialized context. What is the total context consumed across all the agents? This should be fairly straightforward. What is the total token consumption? So 600 is the specialized context plus each of them receive 300. So it is 600 multiplied 600 plus 300 multiplied by 3, which is 900 multiplied by 3. It is not 600 multiplied by 3 plus 300. That's not how it works. This 300 is taken 3 times. Shared base is, although it's a shared base, that same context is appearing as tokens in each API call. Okay, so this is common. So it's 600 plus 300 multiplied by 3, which is 2700. Then a coding assistant uses agents.md file in project subdirectories. How does this relate to context isolation? How does agents.md file in the subdirectory relate to context isolation? So agents.md, which is in a subdirectory, is agent specific. So it defines the context which each subagent receives, right? Agents.md can, of course, be for a specific agent can be modified by the orchestrator for sure. Then when is full isolation the best choice over shared base or sequential pipeline? When do you prefer that instead of shared base or instead of sequential pipeline? This is a classic case where you don't need the agents to know much about what the other agent is doing. They are completely, they're as if they are the only people who exist, like sort of independent contributors in teams. So they are literally in full isolation. Then what is the main risk of the sequential pipeline pattern? We discussed this like 2 minutes ago. So just like how if there is a reasoning, the remaining agents can verify the reasoning. Just like that, there could be a risk of error propagation. If first agent makes an error in sequential pattern, it could propagate into the remaining part of the pipeline. So this we have to put guardrails to make sure that there is an error and it's not getting propagated. So it may result in some extra token consumption to make sure that such a thing does not happen. In a multi-agent system, what is the orchestrator's most important responsibility regarding context? Obviously, the orchestrator's single biggest thing, or rather two things are, one is deciding what subagents you need. Second is once you decide these are the subagents you need, what should we feed to each subagent? So it's deciding what context to include in each subagent's window. Then last question, how do subagents typically share their findings with the orchestrator? So this we already discussed. There is a contract between agent and subagent and the orchestrator agent. Based on that contract, there is a schema that is defined, and that schema will be in JSON format or whatever, and then that will be shared. So this is the quiz. So I need, before we wind up the lecture, there is one more thing. Some people have asked me personally regarding an extension to the weekend assignment. I can already see some assignment submissions that are good. But if you need extension to submit the assignment on MCP, please take few more days if you want. Anyways, I plan to evaluate it after this course only. So I will anyway need some more days to go through your submissions properly. So if you need more time, just take more time. Just let me know, drop me a message. Then I can just take that into a note. So this will bring us to an end of today's lecture. So for the okay, there is a question. Most of the examples are focusing on coding agents. Do these concepts work similarly in non-coding agentic frameworks like LangGraph, Crew AI, Google ADK? Yeah. So the framework of Agents.md, whatever we discussed today, is kind of universal. It works in almost all agentic coding platform as well as platforms like LangGraph. But I am not so sure about the same for the equivalent of Claude.md file, because Claude.md and similar equivalents are there for coding based agents, but for remaining frameworks, I am not sure how it actually works. My takeaway is, if you have access to a coding agent, which is the most modern, you should definitely give it a try. So in the last 3 days, I was talking to 3 separate friends of mine who are working in good positions. And one thing that they have been telling me is like, they have been wanting to use Cloud Code or similar agents, but then there are severe restrictions from their companies, because one of them is working on Amazon, another person is working in 3M. All of these are like $100 billion+ companies, and it's very difficult for them to come to decision of how to use, what to use. So it's very slow. So then what we thought was, okay, for at least to know what are the capabilities, so that they can propose something to their team, so that the team can form a policy which they can see how to implement in their at least in their team itself. What we discussed was, at least for some personal project which has got nothing to do with company, try some of the most modern coding agents. And if the results are like day and night different, at least try to make a proposal to your company about, okay, this is something that we should have. Many of you might have seen people posting on LinkedIn and x.com about their Cloud Code monthly budget. Like some teams are literally, some teams meaning like small companies, like 100 people team, $50,000 bill they are getting for like 1 month's usage. It's like crazy. And many people are literally stopping their operations whenever there is an outage in Cloud Code. But yeah, Sumit's question, how is the experience with auto research? Are the results of experiment improving? Yes, the results of the experiments are improving. But one thing which I noticed is like auto research, at least the way Karpathy has designed it, has a tendency to oversimplify everything. So it is going towards experiments that are too simple. I mean, that's deliberate. Karpath, you can literally see in the in one of the markdown files that he has written, go for simple experiments which can be executed fast. So because of that, one issue is that sometimes the model will not tend towards complex. So if something complex needs to be done, normally Cloud Code can do it, but in auto research, most of the experiments are like 10-minute, 15-minute, 20-minute experiments. But cumulatively, they of course they accumulate to something better. I can see that the results are improving. So one in the paper that we are working on right now, we are seeing that um, uh, they are proposing like from the embedding layer, find out the deviation from the original data and subtract a certain number, which sounds a bit trivial, but it's working. It's really working. So the results are improving, but then my fear is, okay, are we trying something trivial, or is there something logically amazing here, right? So that issue is there. But you should try auto research once. In all of us in our team are running different research problems now to optimize some of our models to see how good auto research can be. So the way you can set it up is take any Amazon EC2 instance. Slightly better RAM would be better. So the free version has, I think, 1 GB of RAM or something, which is too small. Get something with at least 8 or 16 gigabytes of RAM so that things are a little bit fast, at least on the computer side. Then if you have run pod, just recharge it for $10 or something, $10-15, and then connect it with your GitHub. And you don't need to have OpenClaw or anything in this case. Auto research instructions are very simple. Then whatever is your problem statement, whatever your data set or model you have at the moment, if you don't have any model, that's also fine. You just need to mention it. But whatever your problem statement is, mention that, and mention the direction you want to take. And yeah, in auto research, only train.py we can optimize on multiple files. So the by default way he has mentioned it is only train.py will be changed. But the way I have written it is in such a way that I did not directly clone auto research or anything. I gave the link of auto research to Cloud Code, and I gave my own specific instruction. I asked it to follow the philosophy of auto research, but not follow it exactly. Because in my case, I know that experiments, some of them are not 10-minute experiments, they are longer experiments. But I just wanted to follow the philosophy. The philosophy is continuous improvement and relentless experimentation, in the sense like never stop until a human says you stop. So that's the reason why it's 24/7 it's running. Just try that. I also had used one more GitHub repo for research. Forgot the name of that, starting with M. But I am primarily sticking to auto research for next at least few days. I just want to just see what are its limits, how much can it optimize models. But yeah, you guys should try it. Like at least try for some of your research. Try a modified version of auto research. Don't don't clone the repo directly. Just give the link to Cloud Code or whichever coding agent you use. Then mention your instructions. Like you don't want to restrict to simple experiments alone, whatever it is. Just mention that, but follow the similar philosophy. I think that will give even better results. In any case, if I get something amazing, I'll share it with you guys in some days. I'm asking it to run a few more experiments today and tomorrow. All right, everyone, we can stop today's lecture here. Thank you so much for joining and staying back so long. Tomorrow we'll discuss about memory. On eighth session, we will. There are two projects option I'm thinking. I haven't yet finalized because both are equally exciting, but I don't have time to show you both. Maybe I'll record one video, one I'll show in the lecture live, and one I'll record a video or something. But let me finalize it and tell you my plan regarding that. So that will be on Thursday or Saturday. So the date I have not finalized. So the build session will be set on my build session will be on Thursday or Saturday. Raj's and Rajat's build session will be finalized. I'll talk with them and I'll let you guys know the date. Share the explanation of software next week, new course, what it will contain. So that I think Raj will be a better person to answer than me. All I know is like he'll show you some amazing practices for modern software development with AI agents. So I think it'll be a very, very powerful tool. Tool as in powerful framework, which anyone can learn from. So I know Raj's workflow in and out because we literally are working in the same office, right? But I think you guys will benefit a lot from learning the sort of workflow that we internally use at Visuara. So check it out. The link, I can just find the link. Just give me a second. Yeah, so this is the link. Yeah, thanks, Sriharsha. Yeah, that's the link. Just go through that. You should understand the structure. It's starting on next Monday for continuously 5 days, Monday to Friday. So it'll also be again long lectures of building. You will build a lot of projects as part of it. So it'll be like a pure workflow setting up stuff, like how to set up your perfect workflow for building using coding agents. Because there are different things which you need to do for projects of different complexity levels. So for some simple projects, I never define like, oh, go with this project roadmap document with version 1, version 2. I don't say that. I just want things in one shot. But if it's a very complex project, I typically ask to go first be in development mode, develop the V1, iterate on V1. Once that is done, go to the production mode. Planning mode to development mode. And then if it is a good V1, then put it into production, then go back to planning to V2, then planning of V2 to development of V2, and so on. So I have a specific iterative process which I follow for complex, larger scale projects. For smaller scale projects, I don't follow any of that. It's more random. But anyways, you guys will learn all of that in detail on that bootcamp. So see you guys tomorrow. No, it's not self-paced. It is live. It is it's live happening, I think, from 9 a.m. to 11 p.m. I mean 11 a.m. Just let me just share my screen. So this is the modern. I think somebody had shared the link, right? Sriharsha, you had shared. Yeah, I myself had shared. Let me just open that. So this is the bootcamp link, and the goal here is like to have proper build sessions. So you will have to be ready with your laptop and whatever your coding agent platform is. It will not be a passive lecture where you can just listen. So it will be very, very intense, and you will have to spend a lot of actual brain cells to code. But anyways, just if you have any doubts, just drop an email to hello@visuara.com. We will get back to you. But it'll be a very, very nice course. I highly recommend it. Raj has spent a lot of time designing this. So thank you so much, everyone. Let's meet again tomorrow, same time, 9 a.m. And take care until then. Bye.